So far, whenever we've needed to call a function in MATLAB, we've simply typed its name. And that, of course, is the most common way of doing it. But sometimes it's very handy to call a function through a variable instead. A variable that identifies a function is called a function handle. And there are some cases in which function handles are useful. For example, some functions can take other functions as arguments. The integral function, for instance, uses numerical approximation to estimate the integral of any function supplied as an input argument. Another case will come up in a couple of weeks when we show you how to create a graphical user interface, and you'll learn that you can specify which functions should be called when various buttons are clicked. These are termed callback functions, and you specify them using function handles. There are two even more advanced cases. You can actually create a one-line function without a name, called appropriately enough an anonymous function. And the only way to call it is through a function handle. Finally, function handles allow a function inside one M file to call a subfunction inside another M file. And speaking of subfunctions, after we're done with function handles, we'll show you how to use nested functions, which are similar to subfunctions but are defined inside other functions. But we'll get to that later. For now, let's learn how to get a handle on a function. Actually, it's quite simple to create a function handle. You simply prepend the name of the function with the @ character, like this. So now trig is a variable whose type is function handle, and it contains a handle for the built-in sign function. Once we have a function handle, we can use it to call the function. And we can use trig anywhere we can use the sign function with the same result, such as this. And there's a pretty sign function. We can also assign the value of one function handle to another variable. This time MATLAB saw that we did not include an input argument, so instead of using the function handle to call the sign function and copying the returned value into X, it just copied the function handle itself into X. So now we can call the sign function with X. Well, that just looks weird. I think maybe using X as a function handle for the sign function isn't the best idea I've had today. Anyway, to get MATLAB to call the function, instead of copying the handle to the function, just include a function argument. But what about functions that you call with no arguments, like the function pi, which may not seem like a function, but actually is a function, a built-in function. It just doesn't look like a function because it takes no input arguments and returns just one output argument. Let's assign a function handle for pi to the variable myPi. And now let's try to use it to give X the value pi again. Well, that didn't work. To call the function, just include empty parentheses, like this. There. If you want to put together an array of several function handles, you can't use regular arrays. But you can put them into cell arrays. Calling the function through cell array indexing might look a little bit strange at first. This command calls the cosine function with an input argument of 0. It first uses curly braces to select the appropriate element of the cell array, and then uses regular parentheses to provide the input arguments to the selected function. Here's a command to impress your friends. We just called plot by putting a 3 in curly braces to draw the sine by putting a 1 in curly braces from -pi to pi. These aren't particularly useful examples, I have to admit, unless you're into writing code that nobody can understand, for some evil dark net purpose. But we've got some other examples for you that make a bit more sense. Let's start by introducing a MATLAB function named fplot. Fplot is a variant of the plot function, but it takes a function handle as its first argument and plots the function between two limits, which are given in its second argument as a two-element vector. For example, let's plot the sine function from 0 to 2 pi. Well, that's certainly nice, but you might argue that we could do the same thing without a function handle. The good old-fashioned way with plot. Sure, but here we had to provide the actual vector of x values twice, while fplot does all that for us. And it gets better. Look at this example. This time we plotted the tangent with fplot. And here we can see one of the peculiarities of the tangent function. It has a discontinuity at 1/2 pi. The value of the function goes up toward infinity when we approach 1/2 pi from the left, and it goes down toward minus infinity when we approach 1/2 pi from the right. Fplot handled this discontinuity with finesse and even plotted a dashed line to mark it. Very nice. Let's try plotting the tangent with the regular plot function. Not so nice. In fact, it's not even symmetrical. Well, maybe we just didn't use a resolution that was fine enough. Let's try a step size of 1/1000th instead of 1/100th. Oh, that's not it. I think you can see this isn't going to work so well. Certainly not as well as fplot, no matter what resolution we use. So, as you can see, one advantage of fplot is that it handles discontinuities much better. So this is a much better use of a function handle than all that darknet stuff. Let's look at another good example. Let's say we have a polynomial expression that we need to use a few times in our program. We could create a subfunction, but it would be overkill to do that for a single expression, not to mention that we'd need to make up a meaningful name for the function. Instead, MATLAB allows us to create a so-called anonymous function as a single expression and return a function handle to it all in one fell swoop. The only rule is that the anonymous function definition can't be inside a control structure such as an if statement, a switch statement, or a loop. But it can be anywhere else in a function or a script or the command window. Here's an example of the definition of an anonymous function, which happens to be a 4-term polynomial. Let's try our new function using its handle. It works great with a scalar input, and it works great with a vector input. And we can plot it too. Or even better, the syntax is quite simple. The @ sign, followed by a list of formal input arguments, in this case just one, in parentheses, followed by a single expression. No if, switch, or loop statements allowed. The @ and the arguments in parentheses tell MATLAB that we are defining an anonymous function. Its body comes next and is a single expression involving the input arguments, in this case x. The rule for the input argument specification is the same as for regular functions. It's just a comma-separated list of legal variable names. Like this. And we've given it a couple of inputs and taken it for a spin. And the scope of the variables, this x and this y, for example, is local to the expression that makes up the body. Here's proof of that. Here we first gave x and y the values 1,000 and 2,000. Then we called xfn, giving its local variables with the same names, x and y, the values 10 and 12. After the function returned, we checked x and y and found that they still have the same values that they had before the function was called. So the variables outside the function are not accessible inside the function if they have the same names as one of the arguments. So x, x, y, y. On the other hand, all the other outside variables are accessible, as can be seen in this example. Here we assign 10 to c, and then use c in the body of the function, multiplying the argument x by c. So when we call the function and give it the value 3, it gets multiplied by 10. And when I say multiplied by 10, I specifically don't mean multiplied by c. When we define the anonymous function here and use c, MATLAB looked up the value stored in c, found that it equaled 10, and put 10 times x into the actual function, not c times x. That c inside the function looks like a global reference to the variable c outside the function, but it's not. If it were a global reference to c, then if we change c to 11 and rerun the function, we'd get 33, which is exactly what would happen if f were the handle of an ordinary function that made a global reference to c. But that is not what happens for an anonymous function. Here we changed c from 10 to 11, but the function did not change. It still multiplied its input argument by 10. You can even remove c from the workplace, and it'll still have no effect on our function. Unless we redefine it, there's a 10 fixed in the definition of that anonymous function, not a c. I think I'm going to clear things here. At this point, you might wonder why the anonymous function construct is called anonymous, which means literally not having a name. Didn't we give the name f to the anonymous function that we just defined, for example? Well, no. We put the handle for this function into a variable named f, but the function itself had no name. Contrast that with the first example we gave of a function handle. In that case, the name of the function is sign, and trig is the name of the variable that holds the handle for sign. We can drive the anonymity of an anonymous function home by using fplot again. Here we've given fplot an anonymous function whose expression is x plus the sine of x. It plots the function from -5 to 5, and yet there's no name for the function anywhere. So we've seen how to define anonymous functions, and we've seen examples with one input argument and two input arguments. And of course, you can have as many input arguments as you wish. Multiple output arguments are also supported, but in a very limited way. The only way to get multiple outputs is to have the expression that is the body of the anonymous function be a call of a function that already returns multiple arguments. Here's an example. In this anonymous function, the expression is a call of the function max, which already provides two output arguments: the values of the maximum elements in the columns of its argument and the row indices of those elements. The argument to the function is the squares of the elements of the input argument, A. So the anonymous function finds the maximum squared values of the input matrix. If we catch the multiple outputs using the square bracket notation, we get the multiple outputs. If we do not, we get just the first one, as with a regular function. As we said, with anonymous functions, you can get multiple outputs only by calling a function that already produces multiple outputs. But you can get a lot of versatility by using the deal function. Suppose, for example, that we want our anonymous function to return the product and the sum of its two input arguments as two output arguments. You can do it with deal, like this. And let's try it. And as you can see, the product of the two inputs, 10 and 20, is in the first argument P, and the sum is in the second argument S. You can look up deal to see how it works, but it should be obvious that it returns one output argument equal to each one of its input arguments. Well, we've seen how to define function handles both for normal functions and anonymous functions. A normal function has a function name and can have any number of statements in its body. But an anonymous function has no name, and it can have only one statement in its body. Also, if you want to have multiple outputs from an anonymous function, its one executable statement has to be a call to a function that already returns multiple outputs. We put up with these anonymous function limitations because when the function we need to define is just a single expression, it saves us from having to define a normal function. In addition to the three kinds of functions that we've seen so far, the main function, the subfunction, and the anonymous function, there's one more kind of function that we need to talk about. It's called the nested function. What is a nested function? Well, it's similar to a subfunction in that it lives in an M file with a main function, just like a subfunction does. However, a nested function is actually defined inside the body of another function, also called its parent function. The simplest and most frequent use case is when the parent function is the main function, and there's one or more nested functions inside it. Here's our first example, which will help visualize the structure. The main function starts here and is terminated by this end statement. Inside the main function, a nested function starts here and is terminated by this end statement. Finally, a subfunction starts here and is terminated by one last end statement. Oh, and a nested function can appear anywhere in the body of the function in which it's declared, at the beginning, at the end, or somewhere in the middle, as it does here. Its location has no effect on the execution. Ending functions with end statements is optional in an M file with no nested functions, but if one or more nested functions are included in the M file, then every function in the M file must be terminated with the end statement. The end statements are necessary to determine the nesting structure, but it's a rather trivial syntactical difference between nested functions and subfunctions. A far more important difference, a semantic difference, between subfunctions and nested functions concerns scope. Remember that the scope of a variable is the set of statements in which that variable is visible. The usual rule is that each function has its own scope. Its variables are visible to all statements inside the function and invisible to all statements outside the function, whether they be in another function or in the command window. Do you remember us paraphrasing the Las Vegas saying in the first course, "What happens in a function stays in a function"? Well, in the age of social media and nested functions, these rules do not apply anymore. A nested function has access not only to all the variables inside it, but also to variables inside its parent function. Similarly, the parent function has access not only to all the variables inside it, but also to variables inside its nested functions. It's like modifying that Las Vegas statement to this: what happens in Las Vegas stays in Nevada. So why is this good? What's the benefit of this sharing of variables between a nested function and its parent? Well, it makes it simpler to pass information back and forth between the two functions. Simpler, that is, than passing arguments in and out. Let's say that a subfunction would need 10 different parameters to work with. Instead of passing each of these as input arguments, we can make the function a nested function, and it can access the parameters directly. It can also be more efficient when the parent wants the subfunction to change the values in a large array. Again, because it can access the array directly instead of copying values into an input argument of a subfunction and copying the output of the subfunction back to the parent, saving both time and memory. Basically, a nested function and its parent are more tightly integrated than a subfunction and a main function, and as a result they can work together more efficiently. Let's see what's going on in this first example. The main function's goal is to multiply its input x by 10 and return the result in y1, and multiply x by 11 and return that result in y2. So for example, if the input is 3, it should return 30 and 33. Let's see if it works. It does, and it accomplishes its goal by setting c equal to 10, inputting x into the nested function, which multiplies c times its input and returns the result in out. Then the main function assigns that result to y1, and then it repeats the process right here by setting c equal to 11, calling enter again, this time assigning the result to y2. And while it's doing all this, it calls the subfunction named sub a couple times, here and here, to print a message telling us what it's doing. The key feature here is the variable c, which has this bluish-green color. That color is there to highlight the fact that c is accessible in more than one function. It's accessible in the main function, where it's assigned the value 10, and then 11, and it's accessible in the nested function, where it's used in this expression. If you took our introductory course, then you've seen something like this before. That is, you've seen a bluish-green variable that's visible in more than one function. You saw it when we introduced global variables. Global variables, which we mentioned a few minutes ago when we showed that another c in the body of an anonymous function was not a global variable, have both these properties: bluish-green color and accessible in more than one place. In fact, global variables can be made accessible in any function, and even in the command window, simply by declaring them with the keyword global. But we didn't do that here. In fact, as we said in that introductory course, we recommend that you don't do that anywhere without a really good reason, because global variables are so prone to produce bugs. Here, instead of having to use a keyword to make a variable accessible in both the main function and the nested function, we simply assign a value to a variable, say C, anywhere in the main function, and then use the same variable name, C, anywhere in the body of the nested function. And voila, you've got the same C in both functions. Well, there is an exception. It doesn't work if you use C as an input argument or output argument in the nested function. We didn't do that with C, so it is accessible in both functions. So to summarize, in order to make a variable visible in both a nested function and its parent, you assign a value to it in the parent and use it in the child. Let's make that rule clearer with another example. This function sets the variable r, which represents the radius of a circle, equal to 7, and then calls the nested function, named calculate area, to calculate the area of the circle with radius r. Finally, it prints the area. There's no need to give the nested function input and output arguments because it shares variables with the main function. Let's run it. Uh-oh. What happened here? Let me stretch the command window so you can read this error message. And you can certainly read it if you want to, but I can save you the trouble. After all, that's why you're paying us the big bucks. The problem is that we're trying to share circle area between the nested function and its parent without assigning anything to it in the parent. The MATLAB rule for sharing says that the shared variable must be defined somewhere in the parent, and by that they mean that it must be assigned a value somewhere in the parent, and we haven't done that. This rule was added in September of 2019 with version 2019b, which is the version that we're using here. Versions before that would run this code without error. The reason for this rule is to avoid inconsistency, which can happen if there's a function named circle area on the path when we run the function one time and not when we run it another time. The repair that MATLAB suggests is to use an assignment of the empty array to circle area in the parent function. Like this. Well, did you see what just happened? Suddenly circle area turned bluish-green everywhere. The editor has scanned the code. It has noticed that circle area is assigned a value in the parent function, which tells it that circle area in the parent function is a variable instead of a function, and it has noticed also that the same name is used as a variable in the nested function. It thus concludes that circle area is a shared variable and colors it bluish-green to show it. Now let's save it and run it again. This time, no problem. And you might think that we would have to define circle area before we called calculate area. You would be wrong. But I have to say that's what I would have thought too. No, you can put it anywhere. Let's put it way down here. Let's try running it one more time. Works perfectly. And how is this possible? We're using it even before we've defined it. Well, before it runs the code in an M file, MATLAB scans every line in it, just as the editor does, looking for errors and determining the structure of the code. And during this scan, it sees the assignment statement, which again tells it that it should treat circle area as a shared variable. This is a good time to reveal that in addition to assigning a value to it, there's another way to make a variable in a parent function visible to its children. You can include it as an argument. All input and output arguments of parent functions are accessible to their nested functions. Both assigning a value to a variable in the body of a function and including the variable as an argument in the signature of a function serve to define a variable for that function. And thus, MATLAB's rule for sharing variables states that a variable must be defined in a parent in order to be accessible in its child. So, if assignment rule were to have circle area as an argument, we would need to include this superfluous assignment to an empty array. Let's remove both of these assignment statements from assignment rule. And of course we can see that the beautiful blue color of these two variables is gone now. And now let's add circle area as an output argument and R as an input argument. And they both got that lovely color again. Now the function will run without throwing an error. Of course, as my grandmother used to say, the proof of the pudding is in the execution. Well, that might not be exactly how she said it. My memory is a little hazy, but it's definitely true. Let's save it and run it. There's your proof, Grandma. Well, at this point, we've looked closely enough at our first examples that you should have gotten a pretty good idea of shared variables. But what we haven't done yet is look at an example that has a nested function inside a nested function. I'm going to wave my magic wand and make one appear. Abracadabra. And there it is. It's a main function and some nested functions. The name of the main function is simply A, and A contains an assignment to the variable xa, followed by declarations of two nested functions b and d, and it calls the functions show, b, and d. B here contains an assignment to the variable xb and the declaration of one nested function c. So here for the first time we have a function nested inside a function that is nested inside another function. B is a child of A, and C is a child of B, so C is a grandchild of A. Both B and C are descendants of A, and MATLAB allows descendants as deep as you want. Great-grandchildren, great-great, and on and on and on. Although you rarely see anything past grandchildren. C contains an assignment to the variable xc, and D down here contains an assignment to xd. So each function has a variable defined inside it that is named after it. A has xa, B has xb, C has xc, and D has xd. That makes it easy to keep track of where the variables are defined as we talk about them. And so let's talk about them. In particular, let's talk about where each variable is accessible. To do that, it helps to introduce some new computer science terminology. Non-local scope. We talked at length about local scope in our introductory course, where we said that a variable defined in a function has local scope, meaning that it is accessible or visible only in the body of that same function. The other scope we talked about was global scope, which, as we mentioned, is visibility in the body of every function in which the variable is declared to be global by means of a global keyword. Well, the non-local scope of a variable comprises the bodies of every function that is a descendant of the function in which the variable is defined. We don't like global scope because it can be anywhere, but we like non-local scope just fine because it has a well-defined structure. Here, there are just two variables that have non-local scope, and you can spot them by their bluish-green color, xa and xb. xa is accessible in every one of these functions, even c, which is the grandchild of a. The simple way to put that is that the non-local scope of a is b, c, and d. Furthermore, the non-local scope of xb includes b and c, but not d. And xc and xd have no non-local scope at all. They can't because the functions that define them, c and d, have no descendants. There is one more function in this file, the subfunction named show down here. It's included so that when we run A, we can call it to see that the accessibilities that I'm claiming are actually true. Let's run it and see. You can see here the accessibilities of all the variables. In A, XA is accessible. In B, XA and XB are accessible. In C, XA, XB, and XC are accessible. And in D, XA and XD are accessible. And D is called twice, once down here in A and once up here in B. This second call of D brings up a visibility rule for nested functions that we haven't mentioned yet. It's the rule that tells us where a function is accessible, where it can be called. There are actually 3 paths for accessibility. A parent can call a child, as for example here A calls B and D, but it can't call a grandchild, so A can't call C. A sibling can call a sibling, as for example, B can call D. And a descendant can call any ancestor, so C could call B or A, for example. The sibling calling feature is interesting because of the difference from the variable sharing rule. While sibling functions can call each other, they can't access each other's local variables. Access to functions goes up and down and side to side, but access to variable goes only up and down. There's an interesting thing about calling an ancestor too. It's recursive. We didn't include a single example of that because if we did, it would be a recursive call and that would make our example too complicated. As we explained in our segments on recursion, we'd have to have a base case and a recursive case and a conditional statement, and all that would hide the simple nesting structure that we wanted to show here. But MATLAB does support it if you need it. So you know how nested functions work. But what about using them for practical purposes? Well, real-world uses of nested functions involve larger, more complicated programs than our simple examples. But there is actually a relatively simple but useful example where nested functions come in handy. A function can return a handle to one of its nested functions. And it's really pretty cool what you can do with it. Ready to see it? Well, we're not going to show it to you. Not yet. We're going to build up to it. First, we want you to watch me do something in the command window that you've already seen me do. Remember this? We set C equal to 10, defined a function handle for this anonymous function that multiplies C times its argument, and then used the function handle to call the anonymous function with an argument of 3. And we got 30. Remember that? Sure you do. And I'm sure you also remember what we did next. We changed C to 11, called F again with 3, and got the same result. The point was that the C is used to copy the 10 into the anonymous function. So when we change C later, it has no effect on the anonymous function. We even cleared C. So it didn't exist anymore. It still got the same result. The value 10 is baked into the anonymous function. To change it, you'd have to define the anonymous function again. Well, suppose you need to do that, and you need to do it multiple times with different values of C. But suppose also that, like me, you don't want to spend your valuable time defining an anonymous function over and over. Well, you can write a function to do it for you, like this. This function is named getAnonymousHandle. Well, getAnonHandle because it gets you a handle to an anonymous function. It takes C as an input argument, uses it to define the anonymous function, and returns a handle to it, NFH, which stands for function handle, in case you're wondering. And if you're wondering how we can use it, here we go. We first call our anonymous function handle getter with 10, and it builds an anonymous function that multiplies 10 times its argument, and it returns a handle to it, which we put in F10. Then we call it again with 11 to build a new anonymous function, one that multiplies its argument by 11. And to prove that it works, we use the handles that we get to call the two anonymous functions with the argument 3, here and here. And we get 30 and 33. So just as with the anonymous function, the value of c that we called our handle getter with is baked into the nested function that we get the handle to. But this time we baked two functions, one with 10 and one with 11. All right, it's finally time to let you see a function that returns a handle to a nested function. Now here it is. It's called get polynomial handle, and that's because it returns a handle to a function that calculates the value of a polynomial. This function, get polynomial handle, does only two things. It defines a nested function named poly, and then assigns a handle to poly to its output argument fh. So like get a non-handle, it returns a function handle, but instead of returning a function handle to an anonymous function, it returns a handle to a nested function. And that makes a huge difference, because a nested function, unlike an anonymous function, can have more than one command and can have conditional statements and for loops. None of that is allowed for an anonymous function. Let's look at the nested function. Poly sets a local variable named polynomial equal to 0, and then enters a for loop that repeatedly adds this expression to polynomial. The expression references p, which is the input argument of the parent function, and has non-local scope inside poly, hence the bluish-green color. This loop builds a polynomial in x term by term, getting one coefficient at a time from p. So the handle to the nested function can be used to pass in an argument x, and it'll return a polynomial in x based on the coefficients in p. Let's call it. So we have used get polynomial handle to construct a handle to poly by passing in a vector to the argument p, which is referenced in poly. And that vector contains the elements -4, -1, 3, and 1. Let's use our handle to call poly. So that answers the burning question, what is the value of -4 minus x plus 3x squared plus x cubed when x equals 1? And it's -1. Now let's use get polynomial handle again, but this time use a different input. So we have a new handle, pq. Let's call it. So we got a different result. But did this second call, in which the nested function was given a different value for p, have any effect on our first function handle? Let's check. Of course not. It's just like what we saw for the anonymous function. Once you create a handle to a function, the values of its non-local variables, in this case p, are baked in. So that's it for nested functions. But before we leave, let's plot PC and PQ using fplot. We'll plot them over the range from -3 to 2. Well, that's pretty. But you know, all this talk about baking has made me kind of hungry. I need to go find a cookie. But before I do, let's finish by recapping what we've learned. First, we learned that a nested function is a function that's defined inside another function, and that the nested function is called the child of the outer function, which is called the parent. We learned that nesting can extend to grandchildren, and in fact to any number of descendants. And we learned about non-local scope, which means that an ancestor and a descendant can share variables. We learned that a parent can call a child, a sibling can call a sibling, and a descendant can make a recursive call to any of its ancestors. And finally, we learned that a function can return a handle to a nested function. One last note before I get that cookie is that this nesting construct is not new. It was invented 20 years before MATLAB, way back in the 1950s, for a programming language called ALGOL, A-L-G-O-L, which stood for Algorithmic Language. That language introduced a lot of the constructs that we use today, and some that have died out. The concept of the nested function and the automatic read-write accessibility to variables in its ancestors through non-local scope almost died out. In fact, it's not supported by any of the languages C, C++, or Java, except through workarounds. So MATLAB is almost alone in keeping it alive. The purpose of the nested functions is the same as it was when it was introduced by ALGOL a half a century ago, and that is to simplify the passing of information back and forth between functions. It accomplishes that via non-local scope, while avoiding the confusion of global scope and the cost and clutter of parameter passing. And MATLAB's simple syntax and semantics for nested functions does a really nice job of keeping it all simple.